Shadows rise when you hear the call. Shine the light and you watch them fall. Watch them fall with the coming day. Shine the light and they fade away. Well, I let you in, see inside. You will never change my mind. You will never change my mind. Cut your eyes with a rusty tongue. Build your house with the deed you've done. The deed you done got a ringing sound. The deed you done gonna tear you down. Well, I let you in, see inside. You will never change my mind. You will never change my mind. Copper and tin for a shiny skin. Shiny skin, shimmering new. Copper and tin, ringing true. Tolling laws crack my shell. Don't waste your hammer on a broken bell. Broken bell, a broken bell. Don't waste your hammer on a broken bell. Well, I let you in, see inside, but you will never change my mind. Never change my mind. You will never change my mind. Never change my mind. Tall grass whispers, the hills when the wind blows. You stand dreaming deep in the willows. Two boys tumbling, chasing your shadow. Smiling, lost in the echoes. Follow me through tall grass. We could walk for hours. Hide me on this hillside. Maybe we won't make our way back home. Tall grass calls, but I am here alone. The hills have vanished, blackbird is silent, the sea is stumbling. Two boys whisper, father's dying. Tall grass withers, the willows are crying. Follow me through tall grass. Back home. Tall grass calls, but I am here alone. lost cause, but I am here alone. Chasing the days like a lost child, got no time left to play. I wander through the wild, eyes bright and wide, exalted tongue. Love and night come tangle in a shining little sun. Hold to your light, don't ever lose your star. Oh, love, your light is a road to what you are. Both hands in the sky, 2 feet from the ground. One big happy heart for the whole world round. Hold to your light, don't ever lose your star. Oh, love your light.
My name is Sue Wu, and I'm the Earth Sciences Coordinator at OMSI. So I'm going to be your host tonight. I'm super excited to hear today from Dr. Heather Wright. She's going to be talking about the eruption of Mount St. Helens and what it's taught us about volcanic processes and crisis management. And more importantly, where do we go from here? Putting on these shows takes a lot of effort and work. So I want to give a huge thank you to our video streaming partner, Celestream. We wouldn't be able to do this without them. Today, as some of you may already know, is the 40th anniversary of the eruption of Mount St. Helens. And in case you haven't had a chance to go see it, there's actually an art exhibit at the Portland Art Museum. That will be extended until January 2021. But in the meantime, you can check out a virtual tour online. And it's the first ever survey of works of art that examines artists' responses to the awesome beauty and power of Mount St. Helens. You can visit portlandartmuseum.org for more information. I also hope that you've enjoyed the music during the pre-show. We are so excited to showcase our local artists, Portland artist, Tony Furtado. And you can also catch him and Stephanie Snyderman live on Thursday night with their Sidewalk Serenade series. And those are Thursdays at 7 p.m. And you can check them out on Facebook, Instagram, or YouTube. Now, one of the things that we're missing in the virtual science pub is actually the awesome food and drinks that come along with having in-person science pubs. But there are a lot of awesome partners that we've got over in Oregon. So if you get a chance, please get a chance to check out and patronize some of our wonderful partners throughout the state. And you can find them on the list here. All right, so tonight's going to be similar to our usual science pubs that we have in person. If you haven't been to one of those, usually what we do is we'll start off with about 10 minutes of trivia. So you can go ahead and grab a pen and paper, and you can follow along with us on the trivia as we do it tonight. Then we're going to have about a 1-hour lecture with Dr. Heather Wright, who is a volcanologist with USGS Volcano Disaster Assistance Program. And we'll follow that with a 30-minute Q&A. So you can submit your questions on Facebook or YouTube, or you can email us at scienceclub@omsi.edu. And after the lecture, I'll ask Dr. Wright and actually some of our other guests those questions. If you enjoyed tonight's lecture, please consider donating to help support OMSI. If you're interested in that, you can do the Facebook donate button or visit us at omsi.edu/donate to contribute. But don't worry, there's no pressure to donate. Our mission here over at OMSI is to inspire curiosity by creating engaging science learning experiences for people of all ages and backgrounds. So sit back, relax, grab a drink and some food if you have it, and we'll get started. All right. So for today's trivia, we're going to actually be joined by one of our awesome educators, Annie Douglas. And Annie is our early childhood engagement manager. And Annie's coming on, I believe. Is that right?
Yep, I'm right here. Hi, Sue.
Hey. All right. Oh, I guess just can't see you. All right. So Annie, we're going to be doing some trivia questions today, but I was going to ask you a question first, which is, where were you when Mount St. Helens erupted in 1980?
Oh, great question. This is one of my earliest memories. I was 2.5 and I was living just north of Yellowstone Park in Montana, and ash landed outside of our house. And I was so surprised and blown away. And I remember it as clear as a bell, even today.
Wow, that's very cool.
Yeah,
we've got like jars of ash of Mount St. Helens ash from that eruption over at OMSI Science Lab. I was in North Carolina, so I have unfortunately, no Mount St. Helens stories. So what we're going to do next is we're going to start playing the trivia game. So there are 10 questions. So I'll read out the questions, and then Annie, you're going to answer the questions for us, and everyone at home, you can actually answer the questions along with us. So you can write it down on your paper and pen, and you can either, if you want to do it for bragging rights or actually have penalties for chores, you can actually compete with everyone at home too. So what we'll do is we'll do the question, and then I'll give the answer, and then we'll go on to the next question. So Annie, are you ready to get started?
I'm ready.
All right, cool. So, and just a little bit of trivia about Annie. Annie was actually a contestant on the game show Jeopardy!
It's true. Back in 2011. So it's been a while.
Well, was that when Alex Trebek had a mustache or no mustache?
No mustache. That was the in-between years, yeah.
Okay, the no mustache years.
Yes.
All right, so for our first question, how many principal Cascade volcanoes are there between northern Washington and northern California? And the Cascade volcanoes are the line of volcanoes that go from British Columbia down into northern California.
Okay.
And then the answers are 6, 9, 13, or 15.
Okay, well, I think between Rainier, Mount St. Helens, Mount Adams, Mount Hood, Mount Jefferson, the Sisters, which I'm going to count as one, Shasta, and Lassen. I'm getting close to 9, and I must be missing one somewhere in there, or maybe more. So I'm going to guess B9.
All right. So your guess is 9. So let's see what it is. It's 13.
We missed a lot.
I know. There's actually quite a few in that chain.
Nice.
All right. So on to the next question. So of these volcanoes, which is the youngest, most active Cascade volcano? And this is between Mount Hood, Mount Shasta, Mount St. Helens, and Mount Baker.
The youngest, most active. Well, the latest eruption I know about is Mount St. Helens. So I'm going to guess C, Mount St. Helens.
All right, let's take a look. You're correct.
Yeah.
Woo. Okay. Question number 3. Which Cascade volcano is considered one of the world's most dangerous? Is it Mount Hood, Mount St. Helens, Glacier Peak, or Mount Rainier?
Ooh. Between those 4, I feel like I've read, because Mount Rainier is so close to such a hugely populated area, I'm going to guess Mount Rainier just because of the people around it. So
Okay.
D.
Okay, so D, Mount Rainier. So let's take a look. You are correct. And yes, it is. And so it is because of all the large number of people around it. Part of it for Mount Rainier is because it's got so much more snow and ice on it than the other Cascade volcanoes, that if that melts during an eruption, it's going to create these huge lahars, which are these mud and debris flows.
Ooh, yikes.
All right. So question 4, which Cascade volcano erupted shortly before the Lewis and Clark expedition and produced deposits that were mentioned in the expedition diaries? And so you get a bonus point if you can name the deposits. And I'll give you an option of 2 different deposits. One could be lahar, which we just talked about, or it could be ash deposits. And so the options for the volcano that erupted shortly before the Lewis and Clark expedition are Mount Hood, Mount Adams, Mount St. Helens, or Mount Rainier.
Wow. Well, I think I'm still going to stick with Mount St. Helens because Lewis and Clark weren't, geologically speaking, that long ago. They were the early 1800s. So because it's the youngest and most active, I'm still going to say Mount Helens. And let's go with, you said ash or lahar. Let's say ash.
Okay, is that your final answer?
Yes.
Okay, so C, ash. So let's see what it is. Oh, it's actually Mount Hood.
Oh, cool.
Actually, yeah. So it's actually a lahar deposit. So those mud and debris flows.
Okay.
All right. So question number 5: which Cascade volcano is registered as a traditional cultural property in the National Register of Historical Places? Is it Mount Shasta, Mount Jefferson, Mount St. Helens, or Mount Adams?
Wow, traditional cultural property. I wish all of them were. But let's see. I think a large part of Mount Adams is in First Peoples land. So I'm going to guess D, Mount Adams.
Oh, interesting.
I don't know.
So let's take a look.
Nope.
It's actually Mount St. Helens. So C, Mount St. Helens.
Okay.
All right. The next one. Name the well-known feature, which is also a national park, created by the massive eruption of a Cascade volcano 7,700 years ago.
So let's see. Oregon's only national park is Crater Lake. And I think it is a sea caldera.
All right, let's take a look. You're correct.
Yeah.
Yay. So yes, Crater Lake National Park is a caldera. Though I think if you're playing at home and you put down cinder cone, we'll take that too, because Wizard Island, which is in Crater Lake, is actually a cinder cone volcano. So we'll take both C and D for this one. But yay, good job, Annie.
Thanks.
All right, so 7. Name the Cascade volcanoes that received attention in 2001 because geologists detected ground swelling several miles west of the summit. Was it A, Mount St. Helens, Mount Adams, and Mount Hood, or B, Mount Lawson, Mount Shasta, and Medicine Lake, or C, the Three Sisters, or D, Mount Rainier, Glacier Peak, and Mount Baker?
Let's see. Well, the only grouping that makes sense, the way the question is worded, it says ground swelling several miles west of the summit. So the volcanoes would have to be kind of close together. And a lot of these are spread out except for the Three Sisters. So I'm going to guess C, the Three Sisters.
All right. So let's take a look. You're correct.
Yay.
Sisters. All right. What kinds of unusual activity might be noticed before an eruption? So A, an increase in the frequency or intensity of earthquakes beneath the volcano and the occurrence of volcanic tremors. B, changes in the ground surface like swelling or subsidence, which is sinking, or cracking. C, increased steam emissions, melting snow and ice, changes in existing fumaroles or the appearance of new ones. And fumaroles are the vents that gas and steam comes out of, and increased discharge of magmatic gases, I think that's how you say it, or D, all of the above.
All of those seem like great signs of an eruption that might be pending. So I'm going to go with D, all of the above.
Cool. I know anytime there's always a all of the above option, I always want to take that option.
I know.
Let's see if that's it. It is. Yay! All of the above. All right. What drives explosive eruptions? Rapid expansion of water gas bubbles, chemical reactions between magma and rock, friction along magma chamber walls, or rocks falling into a magma chamber?
Oh. What drives explosive eruptions? I feel like water gas bubbles could be it, but I also really like the chemical reactions between magma and rock. Friction doesn't make sense to me. So I'm going to wing it and go B. It's a chemical reaction between magma and rocks.
Okay, so let's take a look.
Sure.
It's yay, the other one you're leaning towards. All right. So it's A, the rapid expansion of water gas bubbles, of water vapor. All right. So the last question, what information was most useful for successful eruption forecasts at Mount St. Helens in 1981? So after the really big 1980 eruption, there is a series of smaller eruptions from 1981 to 1986. And in the photo, you can see that there's a lava dome that built. So there's kind of lava dome building and smaller eruptions during that time. So what was the information that was most useful for forecasting those eruptions? Was it the amount of time since the last eruption, the rate of movement of the dome, the temperature of the lava dome surface, or visibility at the mountain?
It's a tough one. I don't think it's D, because I don't think whether or not we see the mountain matters. C doesn't make sense to me, temperature at the dome's surface. I kind of like the rate of movement of the dome. If it's been moving a lot, like that question about if things are changing or cracking or subsiding or swelling, that might be something. And A doesn't really make sense to me. So I'm going to say B, the rate of movement of the dome.
Yeah, that seems like it makes sense, right? So let's take a look. You're correct.
Oh, hey.
It is. Yay, it's B, the rate of movement of the dome. All right, I can't actually see on your screen, but high five, Annie.
Thanks, Sue.
Okay. I did not tally any points, but you are a winner. I don't know if you were tallying points for this one, Annie.
I wasn't, but I'm going to make my husband do the chores.
Yeah, that sounds good. All right. So thank you, Annie, for joining us. It was fun. So is there anything in particular you're looking forward to hearing tonight?
I'm just really excited to learn more about what we've learned in the 40 years since it's erupted and what the future might bring for Mount St. Helens.
Cool. I know. Yeah, that sounds great. Me too. Thank you so much, Annie.
All right. Thanks, Sue. Bye.
Bye. All right. So let's see. So I'd like to introduce our speaker for tonight. As a research geologist, Heather Wright. Sorry, let me get rid of that. So Heather Wright has spent a lot of time traveling the flanks of volcanoes around the globe, studying ash and pumice deposits to reconstruct eruptive histories and to provide clues about the inner workings of active volcanoes. Her research focuses on understanding what controls the style of eruptions produced during volcanic crises and how to forecast activity prior to an eruption. Mount St. Helens is one of her favorite volcanoes with its numerous explosive eruptions, outpourings of lava, and dome building phases that have both constructed and destroyed its snow-clad edifice over a 270,000-year history. Of particular interest are the multiple eruptions in 1980 and the conditions under which magma is currently stored beneath the volcano. Dr. Wright works for the Volcano Disaster Assistance Program in Vancouver, Washington, which is a partnership between the U.S. Geological Survey and USAID's Office for Foreign Disaster Assistance. Her job involves many functions, including conducting international training courses, participating in volcanic crisis response efforts, and performing fundamental scientific research on volcanic processes. So I'm really excited to have Dr. Wright talk to us today. So I'm going to turn this over to Dr. Wright.
Thanks so much for that great introduction. Okay, let's see, is my slide showing? Should be. Yes. Great. So I'm going to talk to you today about the sequence of events that led up to the May 18th, 1980 eruption, and then the events that followed that eruption. This cataclysmic event dramatically changed the landscape of Mount St. Helens, and the photos here on just my introductory slide show that dramatic transformation quite prominently. This is a view from the north looking across Spirit Lake to Mount St. Helens. So I'll play a video in the background while I introduce the talk. Most of my talk today will be a chronologic look at the events starting in 1980, moving forward till today. But I'll also touch on some scientific questions, and these two science themes include, number one, the science of eruption forecasting. We'll touch on a few lessons learned since the May 18th, 1980 eruption. And then number two, is the understanding that we can learn based on the eruptive products of eruptions from Mount St. Helens. This video shows very clearly a sequence of different rock layers that are products of past eruptions of Mount St. Helens. And importantly, we can learn a lot from these rocks and from the crystals within them about magmatic processes, including storage of magma and ascent toward the surface. Oh, before I move on, I'll just mention that this volcano is known as Lawelatla by the native peoples. That's an important reminder that, that there's a rich cultural history here as well. But before we proceed in this talk, I want to start us all off on the same foot in terms of magmatic process understanding. It's just a series of 3 slides that'll introduce some topics useful for discussion later in the talk. So here you see a cartoon with a question, what drives explosive eruptions? On the left-hand side is a cartoon of what we call an effusive eruption. That is the kind of volcanic eruption that produces a lava flow or a lava dome. It quietly reaches the surface, covering the flanks of the volcano, driven downwards by gravity once it reaches the surface. In contrast, on the right-hand side, this cartoon shows a depiction of an explosive volcanic eruption where the magma is fragmented or blown apart into small pieces that we call pyroclasts or tephra as it's dispersed into the atmosphere. Now, the main difference between these two different eruption styles, which are broad categories, is the ability for gas to escape the magma. So in the trivia that you just saw, you saw that one main driver for explosive volcanic eruptions is the expansion of gas that's originally dissolved in the melt as it moves towards the surface or as pressure decreases around it. This is similar to a bottle of soda that has carbon dioxide gas dissolved in it. You shake up that bottle and you take off the top, gas bubbles, in that case CO2 bubbles, rapidly expand and the bottle overflows. In a case of magma, the gases include carbon dioxide, but the main gas there is H2O or water gas. Now, the difference between effusive or explosive eruptive styles is largely based on the ability for this gas to escape the magma, which depends upon the magma viscosity, that is how sticky is this melt, the total gas content, and how fast magma is moving towards the surface, where if it moves really fast, there's no time available for gas to get out easily. Importantly, as magma moves in this pathway towards the surface, it does several things that allow us to monitor its behavior remotely. One includes the breakage of pathways, so it has a route to make it to the surface. This breakage of rock can cause earthquakes. The movement of fluids through cracks can also cause earthquakes. It also releases gases. I talked a little bit about what those gases are. And then as the reservoir changes in volume, this can cause deformation or movement of the volcano's flanks. And so we use a variety of different volcano monitoring tools to look at these different phenomena, including the release of gas, deformation of the ground surface, changes in the thermal signature on the volcano. So we can use cameras, we can use GPS instruments, we can use seismometers to look for earthquakes or signals of ground vibration or movement, remote ways to see movement of magma beneath the surface. Okay, so I mentioned that one of the science themes that I'm going to touch on today relates to the topic of how we forecast eruptions. Importantly, the forecasting of eruptions does not only involve whether or not an eruption is going to happen, but for an effective forecast, an actionable forecast to take place, we also need to know when that eruption is going to happen, what's going to be produced, and how far the erupted material will reach. Okay, so forecasting includes the first of those three sub-themes, the when. On the short term, that is over days, weeks, months, we rely heavily on monitoring data to forecast the timing of eruptions. So this is a cartoon that just shows a conceptual framework for how eruptive or pre-eruptive monitoring parameters might vary through time before an eruption. You can see we have some hypothetical monitoring parameter shown with the orange line here, which is increasing through time. Perhaps this is seismicity. Perhaps we see an increase in the number of earthquakes per some interval as we move forward in time. Now, there are several different paths that a volcano could take or a period of unrest could take. This might escalate quickly into an eruption, or the activity could plateau for some period of time, moving much later into an eruption, or anywhere along this path, a volcano might go back to sleep and not experience an eruption, or might experience something that we sometimes call a failed eruption. All of these paths have been seen at volcanoes around the world, and so this makes the job of forecasting eruptions very uncertain. The timing and the decision-making often needs to happen early on in a crisis. And because of this uncertainty, we often frame our discussion of discussing future behavior as a forecast, not a prediction. There are many different scenarios that are possible. Indeed, that's also true for the forecasting of what is going to happen. The forecasting what relies heavily on the eruption history of a particular volcano. What I'm showing here is a table where on the vertical left-hand side of this table, you can see a variety of different ages that relate to different stages of growth of the Mount St. Helens edifice. As you saw in the introduction to this talk, Mount St. Helens is about 270,000 years old. It has a rich history of a variety of different styles of eruption. And these different eruptions started out not at a central spot that kept on happening from a single vent location, but over a broad distributed area. In fact, much of the volcano, most of what you can see if you walk up to Mount St. Helens today is less than 4,000 years old. I'm going to focus on that portion of the history. The largest eruption of Mount St. Helens happened about 3,400 years ago, but the evolution as seen in this series of cartoons that I'll show here starts with a broad distributed series of domes, a dome field. And this is what the scene looked like between 3,000 and 2,600 years ago. There was a big landslide, actually a couple of big landslides that dramatically changed the landscape at that time and destroyed a lot of the topography that had been built. But the eruptive activity continued. By 1,800 years ago, eruptive style had changed to something more like a strombolian eruption, which produces, you may have seen pictures of big incandescent fountains, also with ash columns, but also here during this time, many lava flows. Again, notice that they're not all erupting from a central vent. Over this time period, in the year 1479, there was a very big eruption, what is also called a Plinian eruption, bigger than the May 18th, 1980 eruption in terms of the vertical eruption column. And that was followed by, yet again, more eruptions. By the year 1520, again, Mount St. Helens experienced a variety of dacite dome-forming eruptions. That dome collapsed and formed pyroclastic flows, which I'll talk a little bit about later in this talk. By the year 1720, more andesite lava flow-forming eruptions, a dacite summit dome eruption, and pyroclastic flow occurring eruptions occurred. And then in the latest eruption prior to 1980, in 1857, you can see here a sketch across a photograph of Mount St. Helens from pre-1980 to most recent eruptive deposits that include the floating island lava flow on the right-hand side, which you can still see today, and the Goat Rocks dacite lava dome and its collapse products, which were dramatically excavated during the May 18th landslide. Okay, so I've talked about how you forecast what, how you forecast when. The forecasting of where things are going to go also relies on the eruptive history, the type of hazard that we're talking about, and the current morphology or shape of the volcano. If you have dramatic valleys or canyons, that will direct gravity-driven flows in a different way than broad sloping flanks. Now, the potential hazards of future eruptions from Mount St. Helens volcanoes, so this is a focus on what eruptive history can tell us about potential future eruptions. This publication was released in 1978, 2 years before that cataclysmic eruption. And I'll just highlight that in this publication from 2 geologists with the USGS stated that an eruption is more likely to occur within the next 100 years and perhaps even before the end of this century. That's a bold statement for a scientist who's very familiar with the uncertainty involved in these types of forecasts to say, in the year 1978, saying an eruption would happen within the next 22 years. But this is based on what I've just shown you, this rich history of relatively frequent eruptive activity through time, especially in the recent history. Okay, so a forecast for future eruptive activity in the year 1980 includes these scenarios that might include dome formation. They might also include the production of a vertical eruption column, like the cartoon that I'm showing here, where ash, pumice, and hot gases rise vertically from the edifice and then fall down, draping the landscape. This also includes pyroclastic flows, which contain that same material, ash, gas, and pumice material, but in this case, when that mixture is more dense than the air around it, it hugs the topography and is driven by gravity down the slopes, moving at very rapid speeds. It was also known that at Mount St. Helens, the potential for a landslide was possible, something that would dramatically alter the edifice. And in that report that I showed, they also documented evidence for a potential lateral blast. That is, the product of unroofing the volcano that could lead to that hot mixture of gas, ash, and pumice moving horizontally instead of vertically from the newly exposed vent. And then also extensive evidence for mudflows triggered by these eruptions. Again, the variety of scenarios here means that any forecast includes some uncertainty. I'll just take a small moment, just one slide. This is a science talk for a science pub, but since we're talking about a volcanic crisis, the science part of the picture, or even the forecast part of the picture, is only one part of effective volcanic crisis management. In order to effectively manage a volcanic crisis, to make sure people stay out of harm's way, we need a good monitoring network. We need to correctly interpret the activity that's happening at the volcano. We need to provide an actionable forecast, but then we need to be able to communicate that information to the relevant stakeholders, which requires a great partnership with emergency managers and the cooperation of affected population. Although that part won't be the focus of this talk today, you'll see ways in which those other relationships can become really important in decision making. Okay, so we'll start our 1980 picture here in March of 1980. This is an image of Spirit Lake in front of Mount St. Helens. In March, there was no sign of any particularly unusual activity happening until earthquakes started by March 15th. In fact, the first notable sizable earthquakes happened on March 20th with a magnitude 4.2 event, which scientists at the University of Washington noted as being remarkable, the largest such size event in 16 years in this area of the Cascades. And those earthquakes then began to pick up in number and in frequency. Here's a seismograph from this time showing that each of the squiggles on this graph is an earthquake. And so you can see that the number and frequency of these quakes was increasing through time. This graph on the bottom here shows number of earthquakes per day increasing from the 15th of March by the 22nd of March up to 200 noted earthquakes per day. Here's a view of the volcano on March 24th, but that dramatically changed in appearance with the first explosion on the volcano on March 27th. This explosion excavated a crater in the summit of the volcano, so it changed the morphology, draped ash across the landscape. People looked at this ash. Scientists had a look to see what kind of material was contained in that eruption. Here's a video showing one scientist, David Johnston, who's very notable for his expertise during this eruption and the terrible tragedy that happened to him. But here he is providing a really great summary of the interpretation of that ash with this very first eruption during the sequence.
This was not an eruption. This was a steam explosion. That is just hot water, very rapidly expanding, shooting out clay and mud and rock that's up there. No magma has yet come to the surface, but this means that it is heating up, and so magma conceivably is rising. Because this is such a symmetrical volcano, and because the crater is so high, if there's an explosion, it's probable that the debris, the very hot incandescent ash that would come down, could come down all sides. But right now, there's a very great hazard due to the fact that the glacier is breaking up on this side of the volcano, on the north side, and that could produce a very large avalanche hazard. This is not a good spot to be standing.
Okay, so I like that interview because it presents a great summary of the way that scientists try to communicate information through all of these crises. It presents what's known about or the interpretation of the events that just occurred and a forecast of sorts in the scenarios of activity that might follow on from that first eruption. Now, because of all of this increase in activity, the new explosion, scientists came and used a variety of different monitoring tools to try to detect whether magma was moving up towards the surface at a rate that signaled a larger eruption in the coming days to weeks. By April 27th, the side of the volcano looked dramatically different. This is a picture showing the dramatic bulge on the north side of the volcano. Indeed, if we look at a time sequence to look at that dome, that bulge, from March 24th to April 15th, focus on the portion of the image here that is smooth in the March 24th image, but looks very fractured and broken and darker in color by April 15th. That bulge is formed by the side of the volcano moving in order to accommodate magma coming shallowly into the mountain and pushing out the whole side of the volcano. So this cryptodome over this interval began to grow, and it grew very quickly. Furthermore, explosions continued at the summit area, and so very quickly the questions surrounding the hazard and how to manage the potential effects of this hazard became prominent on many people's minds. So here I'll show you a sequence of maps. This is a map of the USGS hazard map as of the 30th of March in 1980. Note importantly here that there's a zone very close to the volcano that could be affected by a variety of different things shown in brown, and that there are many spider-like legs from that central brown area that follow down drainages, and that's the potential hazard zone from Lahars. Now I'll show you overlaying on top of that map the proposed restricted zones for people to not enter, either the red zone or the blue zone here in the 17th of April map. Now the zones here changed in their shape, partly based on discussions of scenarios, but also based on the ability for land managers to close lands. By April 25th, the restriction zones looked something like this. I want to point out, because it'll come back in a later slide, the location of Elk Rock. You'll note in the upper left-hand portion of this image where Elk Rock is, and we'll see a photo from this area later in the talk. By the 30th of April, this was the enacted state of restricted zones. The location of road access closures moved through time, partly to reflect the understanding of hazards as presented in that hazard map, but then as people became moved back and forth as managers became nervous about the potential for hazard, and then as political forces tried to push back against closure of areas where people made their livelihoods. So this zone was actually proposed to extend to even much greater distances, but this increased blue zone restriction was never enacted before the 18th of May eruption. Okay, so now as we're moving forward in time, we see a series of explosions, a series of the sides of the volcano being pushed out, so a bulge forming. What were the other measurements or monitoring data telling us? If you look in the lower left figure here, you can see on the x-axis of this figure from May 4th to May 18th, some line measurements that show deformation in meters per day, so rate of deformation of that bulge as it was growing. I mentioned that one possible scenario for the way eruptions have progressed at other volcanoes through time is some increasing in a monitoring parameter that escalates or that accelerates prior to the eruption. And many scientists thought that that might happen. There'd be an acceleration in the rate of deformation before any sort of major landslide at Mount St. Helens. You'll note that we don't see that. The curve doesn't get really steep right before May 18th. Similarly, if we look at the rate of seismicity, the graph in the lower right shows focus here, maybe just focus on the black line, which is the number of seismic events per 6-hour windows moving through time. And this is for seismic events of a magnitude of 2 and greater. And again, just to point out that there wasn't any huge spike in the number of earthquakes around the time or just preceding the May 18th date of this big eruption. So again, a forecast of the timing of an eruption has some uncertainty. There are certainly signs of some change in the state of the volcano, of pressurization, of magma movement, but it's uncertain the exact timing of when that magma will cause a larger eruption because there's no short-term escalation in these parameters around this time. There's also, though now we're reaching on almost 2 months of activity and weeks of people being restricted from accessing different areas. And so people were pushing back, they were frustrated, they were tired. Harry Truman famously stayed at his place on Spirit Lake. On May 17th, there was enough pushback that 35 people were granted access by signing a liability waiver on a police cruiser in order to access their homes to collect belongings that they wanted to take out of their summer houses and bring back to their homes. But now we'll move on to what happened on the morning of May 18th, which was a clear day. At 8:32 in the morning, the sequence begins. Luckily, this was not May 17th. This wasn't the time that all these people were going back to their houses. It was early enough in the day that there weren't many people near the volcano, especially in the restricted access zones, although, as you'll see later, there were people outside of the restricted access zones that died that day. We'll start with this video here, which shows the sequence of events that started this all off, starting with an earthquake, landslide, a magnitude 5.1 event. Here's the landslide of the whole side of the volcano falling away, sliding away, which immediately triggers this big blast of pumice and ash and hot gases. And you can see that it's moving not just up, but to the side. And so those are the first 2 events. I'll note that these are amazing photos by Gary Rosenquist that help us piece together what happened there, along with several other photos from around the volcano. So the sequence of events started with a landslide, or what we call a debris avalanche, that moved quickly away from the volcano, 70 to 155 miles per hour, fast enough that that chunks of the volcano, or what formed these hills or hummocks in this photograph here, actually made it up and over some ridges north of the volcano, reaching up to 14 miles away to the northwest of the volcano. Closely following on the heels of that landslide was the lateral blast. And it had such power, such force, that in the immediate area around the volcano, it decapitated trees, taking them with it. It then downed trees, pointing them all in the direction of flow away from the volcano. And then it singed trees in an area even further away. This was moving even more quickly at over 220 miles per hour, so fast that even though the debris avalanche or the landslide started first, by the time these 2 phenomena reached about Coldwater Lake, the lateral blast actually overtook. It got fast. It actually reached ahead of the debris avalanche. And this lateral blast reached very large distances, 17 miles to the north-northwest, felling timber and causing great devastation. So one first lesson learned here is I mentioned that it was known a lateral blast was possible from something like a landslide at Mount St. Helens, but the scale of this lateral blast was so much larger than anticipated. Then after that lateral blast, a vertical eruption column formed and grew through time in its volume. It reached over 30 kilometers above the mountain, and the ash that was distributed into the atmosphere circled the whole Earth in 15 days. It reached great distances, distributing over 10 inches of ash at about 10 miles away, an inch of ash at 60 miles away, and a half inch of ash, which is still quite a lot, at 300 miles away. Here are some images of that vertical eruption column, which persisted for hours during the day of May 18th. Here are some images of the ways in which this ash and pumice cloud turned a gorgeous sunny day sky into what looked like a night sky. The image in the lower right is from Ritzville in midday. The street lights came on because the light was so low. The stuff that was distributed, the products include ash and aggregates that we call accretionary lapilli, where ash accumulates around moisture droplets in the air. It accumulates in concentric circles. Although this image isn't from Mount St. Helens, this is what a lot of these accretionary lapilli looked like close to the volcano. And that sediment, or that pyroclastic material, was distributed, covering the landscape largely to the east of the volcano. Now, that vertical eruption column, as I mentioned, lasted for hours, but by about 3 hours after the eruption started, a portion of the column started to collapse, forming large pyroclastic flows. So as I said before, pyroclastic flows are the same mixtures of ash and gas and pumice, but it's denser than air, and so it follows topography, hugging the ground surface. Again, these are fast-moving, 50 to 80 miles per hour. They're very hot because the transporting material is gas, but it's magmatic gas, so it's over 700 degrees Celsius. The deposits from this from this phase of the 1980 eruption produced thick piles of pumice and ash. This is a photo of mine from a couple years ago. Now the pumice plain down at Mount St. Helens has been eroded, so we can see a big thick section through the material deposited by that May 18th pyroclastic flow. You see these people for scale, not just those in the foreground, but those in the mid-distance as well. And then, although small lahars were triggered almost right away, very large lahars were triggered in the afternoon of May 18th by dewatering of the landslide deposit. So groundwater that was within the rock material dewatered and fed these big mudflows or lahars that moved down river valleys. These make slurries of something kind of like a cement-like mixture, very thick, also moving very quickly, can be very erosive, and moving at such speeds, carrying all this debris, including logs. Here you can see in the center there, even trucks, that they were able to destroy bridges. There in the lower left, you can see a picture of the bridge, a damaged, destroyed bridge in the lahar from May 18th. In fact, these lahars down the Toutle River reached all the way to the Columbia River, 100 kilometers downstream, and they put so much sediment, so much ash and debris into the Columbia River that they made the Columbia River uncrossable where the Toutle River entered, and stranded 31 ships in upstream harbors. This graphic shows some of the devastation. This is a graphic from the Columbian newspaper. Although the details are a little bit off, in general, I show this just to show it, a diagram showing the distribution of people that died. All those numbers are the best representation at this time of where people were thought to have died, mostly from the blast of this eruption. And so many were at great distances from the volcano. Many probably wouldn't have even had a direct view of all the activity happening at the crater itself. Here we can see an even enlarged view of those lahars that made it all the way down these rivers, down the Toutle, which feeds into the Cowlitz, and deposited sediment along their links. This devastation and recovery took a long time. The rescue efforts required the efforts of many, many people. As you saw on May 18th, visibility was 0 in many proximal areas. You can see some of the devastation here in these images with all of the brown, murky water in the rivers, providing some insight into all the debris, all of the sediment that had been transported down in lahars. You can see President Carter here in the lower left. And this is just to speak to the scale of the tragedy, the 57 people total that died in this May 18th eruption, the dramatic consequences of this big eruption. And I'll just add a little bit of an aside here that the consequences of that big eruption didn't end on that day. In fact, the large amounts of sediment down the Toutle and Cowlitz rivers required a huge dredging effort to move the sediment to allow shipping channels to reopen. That dredging produced big terraces of dredged material. There also was a sediment retention structure built to trap sediment upstream, and that continues to be a long-term mitigation issue, how to deal with all that sediment. But I'll just mention we're not stopping here with May 18th. And so as recovery efforts and response efforts were taking place over the days after, activity continued at the volcano. And so monitoring needed to continue as well. Before we move on, I'll just move us through a time sequence here, starting pre-May 18th with the volcano. We had that dramatic event, a landslide, a blast, a vertical eruption column, pyroclastic flows, and lahars on May 18th. But that continued through time. Activity continued with another eruption on May 25th, vertical eruption column, another on June 12th, producing a vertical eruption column and pyroclastic flows. After the June 12th eruption, a dome began to grow in the new crater of Mount St. Helens. And then again in mid-July, July 22nd, there was another explosive eruption that again generated pyroclastic flows, where this time the pyroclastic flows reached shorter and shorter distances from the summit area. In August 7th, again, an eruption with a vertical eruption column and pyroclastic flows, again followed by dome growth. And October, mid-October, yet again, where the dome that followed that explosive eruption then became a persistent site in the crater over the next 6 years, with episodic growth and punctuated smaller explosions. So here's a picture of the 1980 dome. Okay, so I'll pause just here for a second just to say that as activity continued, its style changed, but the challenge remained to forecast eruptions and to try for scientists to understand the behavior of the volcano. And while there were some particularly big challenges with forecasting that May 18th eruption, there were some really great successes in the forecasting of eruptions, especially in 1981 and in 1982. So a dome continued to grow for years after the May 18th, or after the October eruption of 1980. And in this particular case, you can see, here's just an example from March of 1982. And this is a plot on the left-hand side, which shows a variety of different monitoring parameters that include one way to visualize seismicity, that is a seismic energy plot, measure of dome expansion, where you can see the rate of expansion increase through time. So we have a rate of seismicity increase, a rate of expansion increase, tilt or inflation increase in the dome. And all of these are accelerating towards an eruption. And you can see that the scientists in this particular case, and in over 8 eruptions over 1981 to 1982, had amazing success with these predictive windows for their forecasts of eruptive activity, where the successive predictive windows saying an eruption would happen somewhere over this time narrowed in their time window as the scientists approached, or as time approached the time of the eruption. And so these monitoring strategies were very useful for this semi-stable behavior of slow dome growth and punctuated explosive activity at the volcano. Okay, so already pointing towards a couple of lessons learned from the eruptions up to this point. We learned about eruption forecasting, a variety of different eruption triggers, where in the case of the Mount St. Helens May 18th eruption, the trigger for that eruption was the landslide, the essential uncorking of the volcano that led to a much more dramatic eruption and the cataclysmic change to the landscape surface beneath. But other eruption triggers included these pressurization events that led to repeated forecastable or even predictable explosive events within a dome sequence. We also learned a lot about scale of hazards, especially for lateral blast hazards. And here's a picture. Oh, I mentioned that I was going to tell you that Elk Rock, which I noted the location of, this is an image of the blast at Elk Rock there, or just south of Elk Rock. Other lessons learned. We learned more about the magmatic system using other tools, remote monitoring tools, and the products of the eruptions themselves. So we developed this picture of the magmatic system after May 18th, 1980. And this picture is a composite of information based on earthquakes or seismic activity. Earthquakes, in this case, are shown in the stippled pattern here, where earthquakes occur in the brittle crust that surrounds the magma zone itself. And so essentially that shadow zone where earthquakes aren't occurring is inferred to be where magma is stored. And this conceptual model of where the largest portion of magma was stored beneath the volcano is consistent with information we know from crystals within the pumice and the eruptive products, where here people did experiments looking at the composition of crystals found in these magmatic products and matching the pressures of experiments and the compositions to the compositions actually seen in the natural products. And so you can see an arrow pointing there to the depths inferred by some of these experiments for the May 18th products. We also learned stories. We also learned information about the magmatic system from the crystals within these eruptive products. So a very quick primer into how crystals form. For those of you who've taken geology, probably your initial introduction to crystallization of magma was from cooling of magma, where the schematic figure I show here shows a temperature and pressure variation. As the material cools, it moves from liquid to solid. On the left-hand side, I show some images of slices through lava from Mauna Loa volcano, where the one on the upper portion of this figure is from Mauna Loa lavas that cooled very quickly, and the one on the bottom shows lots of tiny little gray-shaped rectangular things. Those are crystals, and that's a lava that cooled very slowly. But I'll just add that magma does not only crystallize in response to a temperature decrease or cooling. Magma also crystallizes as it ascends or as pressure decreases. So we can move from liquid to solid as pressure decreases. And again, the rate at which that occurs, how fast you move from liquid to solid fields, can control the textures of the rocks or how big the crystals get. If magma ascends very slowly, you get very few but large crystals. The faster it moves towards the surface, you get many more small crystals. And if it moves fastest of all, then it's just glassy with no crystals at all. Okay, so let's look again at our Mount St. Helens 80 to 86 sequence. If we look at the products of eruptions from May 18th, 1980, compared to those from later eruptions that were dome forming, we can see a dramatic difference. The May 18th eruptive deposits have no, the pumice has no crystals, no small crystals at all. This is all glassy material with bubbles. The black is bubbles and the gray is glass. In contrast to the dome material, which here again, bubbles are black, The gray is glass, but all of these rectangular shaped things are small crystals. And these crystals tell us a story that's linked to how fast magma rises before these eruptions. That big cataclysmic eruption of May 18th, 1980, magma rose from the storage region very, very quickly during eruption. In contrast, magma rose very slowly to reach the surface in domes and the small explosions later on in that sequence. What else have we learned about Mount St. Helens based on the eruptive products, and in this particular case, from the crystals? Well, here are some more images of slices through volcanic rocks. In this case, this is ash from pre-May 18th, 1980. You recall the video of David Johnston saying that their best estimate of what was in that ash was that it was just old rock. One of the reasons they said it was old rock is that it was very, very crystalline. It was very dense. It looked like something that was not fresh, bubbly magma. However, when scientists later, in a study tens of years later, looked at this material and compared it to the same material that was found in Mount St. Helens May 18th deposits from the cryptodome, that shallow material that was sitting, pushing out the sides of the volcano. If you just look at the texture, the shapes of the crystals in these two different images, they're hard to distinguish between each other. In fact, they're just the same, which tells us that that ash from pre-May 18th was actually brand new magma. It's just that we hadn't done this kind of study before and didn't know what signs to look for that would tell us the story of new versus old magma. So another lesson learned is a great insight into how crystals tell us information about when new magma reaches the surface. Okay, I have just a few minutes left in the talk. The story doesn't end in 1986. That episode of eruptive activity between 80 and 86 was followed by eruptions in 1989 to 91 that many people forget about. These eruptions did not contain new magma. They were just steam eruptions. They were followed, though, by another sequence of magmatic eruptions between 2004 and 2008. I'll just touch briefly on that sequence, which started with an earthquake on September 23rd of 2004 and was followed by increasing seismicity. The plot that I show here is from the 27th of September to the 30th of September, and you can see an increase through time in number, size, and rate of seismicity at the volcano, escalating fairly rapidly over several days. Again, we'll touch back to that question of forecasting of eruptions. Our same scenarios exist because we're using the eruptive history to inform the future. Although I'll add the caveat that some modification to the scenarios is added here because the shape of the volcano is so dramatically different. And so a large landslide is certainly not possible to the same extent that it had been originally because of the vent being in the center of this now wide crater-shaped depression. So the 2004 sequence moved to explosive eruption on October 1st of 2004. You can also see cracking of a glacier here in this photo, which led to or was followed by growth of a dome. Here you can see a picture of this big dome, this whaleback dome with a smooth surface, very different in texture than the 1980 to 86 dome, covered with a veneer of fault gouge as it slowly extruded, actually sometimes quickly extruded out of the ground. The largest of the sequence explosive eruption included that of March 8th, 2005, which dusted ash across the flank of the volcano, but was nowhere near as big as any of those big vertical eruption column and pyroclastic flow producing eruptions that I showed earlier in this talk. Dome growth continued, producing a big new lava dome that lies to the south of the 1980 to 86 dome, in between that old dome and the south crater wall. I'll also point out that this eruption caused deformation and movement of the crater glacier within the crater of Mount St. Helens. This is just an interesting aside. That deformation of the glacier has caused advance of the glacier. You can see the two arms of the glacier moving forward here. They're now joined today, and this is a very rare case of an advancing glacier in today's climate. Okay, so to round out this talk, we now have a sequence of eruptions through time. We have a picture of what the magmatic system looks like. We know something about the rate of magma ascent leading to different eruptions, where some cases we also know where magma came from in these eruptions based on the crystal population. Let's see, 80 to 89 did not have any new magma, so I haven't shown an arrow there at all. I'll also just add, because I think this is of interest in the recent history, in 2014, the USGS released a statement saying that there are signs of repressurization since 2008 caused by arrival of a small amount of magma at these kinds of 4 to 8 kilometer depth range that don't indicate the volcano is likely to erupt anytime soon. Although I add this star and the note for this information statement in 2014, this isn't the first time this has happened either. There were signs over this intervening interval also of pressurization of magma chamber. It's part of the normal cyclicity of the system at Mount St. Helens and at many volcanoes. Okay, so in summary, I'll just end with some lessons learned since 1980. This was a relatively short talk, and I couldn't get to many of the other lessons learned, but I touched on some of the aspects of the science of eruption forecasting, lessons learned about the nature and size of both the debris avalanche and the lateral blast hazards. Certainly by looking at the shape of the debris avalanche with the hummocky topography, we found analogies around the world, including at places like Mount Shasta, which show those hummocks as signs of past debris avalanches or landslide there. We also learned about the scale of the lateral blast hazards. We learned about triggers for eruption or explosion onset, which could be because of unroofing or uncapping of the volcano, an external trigger, or could be from internal pressurization of the volcano, like happened many times during the sequence that produced domes and explosions later in the 80 to 86 sequence. We also discussed that there's always going to be uncertainty in these forecasts because these are inherently complex systems, and there are many scenarios for ways in which the evolution of the sequence can occur. This remains a difficult part of volcanic crisis management. Certainly, it's part of the equation for making decisions for risk managers as well. And then finally, we talked a little bit about lessons learned from the science part, the stories that crystals can tell, including things like depth of magma origin, which when combined with the monitoring data might produce a picture of what the actual shape of the magma chamber looks like. Although I couldn't get it to it today, there are ways in which petrologic information, that is chemistry of the crystals themselves, are combined with monitoring data in the very recent past to tell us even more information about the timing of when recharge might occur. And we used crystals to learn something about the rate of magma ascent and signs of new magma. So where are we moving forward? These are just a few lessons among the many that have been learned both in May 18th, 1980 and on all the years since then that'll help us better forecast eruptions. I show on this slide a graphic of a simplified version of the hazard map for Mount St. Helens, showing different zones with a variety of different hazards described succinctly here in the lower right corner, including some of the phenomena that we've already discussed today. What does the future hold? Something like 7% of the mass of the edifice that was lost on May 18th has been replaced through these consecutive dome-forming eruptions. The future will inevitably include both lava dome formation, maybe or maybe not, also lava flows, and this will eventually rebuild Mount St. Helens. In order to figure out when that might happen, we continue to monitor the volcano. We use a variety of different tools, many of which I didn't have time to talk about today, to help us figure out what's happening inside the volcano, to help us see into the parts that we cannot visit. And of course, in the USGS, which is where I work, as I mentioned before, an understanding of the hazards is only part of the effective crisis management. So we continue to work with partners on all the elements of communication and crisis management and crisis response planning that we can, with communication in a variety of different forms on the web, in Facebook, community meetings, and response plans, and that kind of thing. So I'm just going to leave you with a video. This is my last slide of the talk. This is a video of the modern Mount St. Helens of 2 USGS scientists on the dome, making measurements, looking to see what the gases that are being emitted can tell us about the magmatic system. And the video footage is from a drone, an unmanned drone. The technology here, both in the equipment used to monitor the volcano and in the equipment used to make measurements, to take videos, is improving all the time. And so we have this great opportunity to continue to learn about the system and to continue to see how the landscape changes from here on out at this magnificent place. So thank you so much for listening. And yeah, I think I will end. Oh, here's just a final image of 2 other USGS scientists working on station maintenance, again with Spirit Lake in the background. So thank you.
Thank you so much, Dr. Wright. That was so fascinating. It's amazing how much work has to go into like trying to forecast, understanding what happened in the past, and also trying to forecast for the future to reduce that risk to people. So thank you so much for your lecture. I really appreciate it. We are going to go to the question and answer portion of our talk. And we're going to be joined by actually 2 more scientists from the USGS. Seth Moran, Dr. Seth Moran, and Dr. Mike Poland. And Dr. Moran, I might have you, if you wouldn't mind introducing yourself first.
Sure. I'm a seismologist by trade. I've been at the Cascades Volcano Observatory since 2003, and for the last 5 years have been serving as the scientist in charge at CVO.
Great, awesome. Dr. Poland, if you wouldn't mind introducing yourself.
Sure. Hi, everybody. I'm Mike Poland. I'm also at the Cascades Volcano Observatory. My specialization is in volcano geodesy, which is the shapes of volcanoes and how those change. And I'm currently serving as the scientist in charge of the Yellowstone Volcano Observatory.
Cool, awesome. Let's see. So we've got questions that have been coming on through comments in Facebook and YouTube. And I'll just mention that Dr. Moran is also doing 2 jobs at the same time. So if Dr. Moran's looking in another direction, he's just monitoring another page that's going on. Let's see. So I'm going to start off with a definitional question, which is, what is a lahar?
A lahar is a volcanic mudflow. So this is a slurry of volcanic material, including ash and water. Water's the transporting medium here. You probably heard in the trivia discussion of the very large lahars that are possible at Mount Rainier, where melting of glacier ice would add a large volume of water to any other erodible material in that volcano.
Cool, great. Let's see. So for the second question, this is from Gabriel, who is age 8. Hey, Gabriel. So Gabriel would like to know if scientists are currently monitoring temperatures on Mount St. Helens, and if so, how hot is it?
That's a good question. We don't have any instrumentation out at the volcano right now that's monitoring it continuously. There are times when scientists go out and measure temperatures of existing steam vents, and that video that Heather showed in sort of the last part of her talk showed some of those steam vents, and that's an area that stays snow-free year-round and is the place where people are measuring right now the hottest temperatures, and those temperatures have been cooling a little bit over time, and that's because it's sort of lava that was erupted in the 2000s that is continuing to cool.
Do you have just a follow-up question? Do you know about how hot, like if magma was flowing out, about how hot that would be?
So the magmatic temperatures would be in the neighborhood of 750, 800 degrees Celsius. And to the best of my knowledge, and Heather and Mike, please correct me if you think otherwise, the temperatures that have been measured out at the fumaroles are more in the order of, the peak temperatures have been more in the order of maybe 150 degrees centigrade, something like that.
Great, thanks. To follow up with another Mount St. Helens question, is Mount St. Helens still active and will it likely erupt again? If so, when?
Who are you pointing at, Heather?
I suppose any of us could answer this. Yes, it's definitely still active. When will it erupt? We don't know. There aren't signs of imminent eruption. There aren't any signs saying we're escalating to an eruption right now. Certainly, it has a frequent eruptive history. You saw in the introduction to the talk that I spoke of many different eruptions over the past several hundred years. And there are signs, as there have been for a long time, that there is still activity happening beneath the surface. So yes, there'll be well, most likely there'll be another eruption. When it'll happen, we don't have any signs of it happening anytime soon. But again, this is the most frequently active volcano of the Cascades, so it probably won't be a huge amount of time in comparison to other volcanoes.
And also just add to that on September 22nd, 2004, we were in the same situation we're in now, where nothing was happening. We saw these sort of deep earthquakes, and people were thinking years to decades, and then the next morning there was a swarm, and 7 days later, 8 days later, there was an explosion. So, which isn't to say that I think it's going to happen tomorrow, but when St. Helens does wake up, it can happen very fast. And what we've learned now twice is that it's really important for us to keep our eye on the prize and keep working at the volcano, keep monitoring it, even if it seems like nothing's happening, just because very real possibility that it could start up again.
Let's see, so I kind of have a related question to your answer. So if earthquakes are a sign of potential eruptions, could earthquakes in turn cause eruptions?
Well, I'll take that one as the seismologist. So there is this story that Heather touched on about the initiation of the May 18 event, and whether that was caused by an earthquake or whether the earthquake was a landslide. That's sort of one kind of extreme example of that kind of a thing. And in the case of Mount St. Helens, the events happen so close together that we'll never know which started things. But on a more global scale, it's certainly a very natural question to wonder about. Hey, there's a magnitude 8 or a magnitude 9 that just happened 100 miles away from this volcano. Is this volcano now more likely to erupt? And it turns out scientists have looked at this question, and at least in the short term of looking at a week surrounding a large earthquake, that if you look at the volcanoes and their activity level the week before that big earthquake, and then a week after that earthquake, that there, statistically speaking, is really not much of a difference in terms of eruptions occurring right after a magnitude 8 or 9. It's not to say that it hasn't happened, but it's not a very likely thing, and statistically doesn't rise to the level of something being something that we would be worrying about here in the Cascades should we get our next magnitude 9.
Let's see. So for the next question, what kind of improvements have been made in the prediction of volcanic eruptions?
Mike?
Yeah, you mind if I take that one?
Go for it.
Prediction is a tough nut to crack because it really means getting the time, the place, and the magnitude of the event. And the best predictions actually in volcanology still are of the 1980 to 86 dome building eruptions that occurred after the big May 18th blast. The Cascades Volcano Observatory in the 1980s made some really accurate predictions. In terms of forecasting and looking at what may happen at a volcano, that's getting a lot better as well, especially the timing of these events, because of all the data we have access to and the information that we've gotten by looking at volcanic eruptions over the last many decades. So I think we've actually gotten pretty good in a lot of cases at forecasting the timing of eruptions based on just incredible amounts of data that are flowing in. You know, back in Mount St. Helens days in 1980, we were looking at, for measuring deformation, lasers, bouncing lasers off the dome or the growing bulge on the north flank of St. Helens. Now we have continuously monitoring GPS stations that can detect millimeter scale motion 24 hours a day, 7 days a week, regardless of weather. And we have satellites that can detect millimeter scale motion, whether or not there's clouds, day or night. So the scale of the technology has improved so much that we have the data we need in many cases to be able to make forecasts that, in terms of timing, are not too bad. I think one of the real challenges we face, though, still is trying to understand what might actually happen. Is it going to be a large explosion? Is it going to be a dome building eruption? And that's still where we may not have all of the understanding we need to get really accurate forecasts.
Can I add one thing to that? Yeah, so one of the slides I showed in my talk, which was mentioning effective volcanic crisis management, touched on two of the things that Mike just mentioned. One is having a really good network of instruments. And so Mike touched on all the improvements in these monitoring, in these tools for monitoring. The second was a correct interpretation of the data. And as we improve our models of volcanic systems, of the processes at work in these magmatic systems, hopefully we're approaching more and more accurate interpretations. I think both of those things help us to do things like better pattern recognition of the signs that lead towards eruption. But we will always have a hard time with those eruptions that are triggered by external factors, that erupt for very long periods of time, and so have oscillations or changes in the degree of explosivity. Understanding the timing of when things changed after the throat of the volcano is already open. Some of these things are much more difficult, and so there will always be cases of things that remain really, really hard to forecast.
Great, thanks. Let's see. I'm assuming this has to do with pressure. Would it be possible to drill into a volcano and vent the gases?
I can take a stab at this one. This is actually a question that we get quite often with regards to Yellowstone. Basically, can we drill into the volcano and sort of let off the pressure, let off the gases? And it's not, it seems like it should work, but it's not really that simple for a lot of reasons. One is that the scale of the magmatic systems of these volcanoes are really beyond comprehension. You can't just sort of drill into something like you're going to pop a balloon, because the magmatic systems are just huge. And the other aspect is that it's not like trying to relieve pressure or gases that are maybe in water, where the fluid isn't not very viscous. It's not very sticky, and so the stuff just wants to come out. Instead, you'd be drilling into something that is very viscous, very sticky, and the gases don't want to naturally come out of this stuff anyway. It's really, you have to decompress huge amounts of it by bringing it up closer to the surface or doing some other things in the magma body itself. So it's not really feasible. We don't really have geoengineering kinds of solutions to prevent eruptions or to let off the pressure or let off the steam, so to speak, just because of the character of the magma and the gases in the magma and the scale of the problem. It's really, really massively big.
Yeah, I mean, I think in some introductory volcanology textbooks, there are some old pictures that show a pocket of gas somewhere. Unfortunately, that's not what the system looks like. In many cases, it's a distributed network of bubbles through a molten magma that's at super high temperatures. And so first, you would need to find a way to connect all those bubbles together, make a permeable network, and then also make a tool that can survive 800°C temperatures and tap into that network. And those are all just impossible things.
All right. Let's see. The next question is about Mount Hood. Is there a forecast for Mount Hood?
Well, Mount Hood is a different volcano than Mount St. Helens. It's erupted a lot less frequently than St. Helens has. Its most recent eruption actually wasn't all that long ago. It was 1781 to about 1792. So imagine that, having ski areas and Highway 26 and whatnot, all kind of in a place where it was living with an eruption for about a dozen years. But before that, it was about 1,500 years, and then before that, it was thousands of years till the most recent eruption. So it's not had a whole lot of eruptions in its the recent time frame. And so if you use the geologic principle that the past is the guide to the future, Hood is maybe not the place that we would look to first as being the most likely place to expect it. But that being said, there are a lot of earthquakes at Mount Hood, or actually more off to the south. And those have included earthquakes as large as a magnitude 4.1 back in the early 2000s that a lot of people felt up there. And so from the perspective of seismicity, it's an active system. And along with Mount Rainier and Mount St. Helens, those are the three places that we most commonly see earthquakes in the Cascades of Washington and Oregon. And so from that perspective, it's alive and well and well worth watching. And then also it's a volcano that that emits magnetic gases. And there's a crew from CVO that's gone up there every couple of years to sample those gases and sort of monitor the compositions that are coming out. That group is also working towards establishing a real-time sensor up there that will be tracking gas chemistry at a sort of 10 minutes or even more frequently kind of a thing. So the long and the short of it is it's an active volcano. It does show signs that it's alive and well, and it is definitely a system that's worth watching. But relative to Mount St. Helens and its eruption frequency, Mount Hood isn't quite in the same ballpark.
Yeah, I'll add one other thing because I'm seeming to add something. Part of a forecast is also the what is going to happen. And as Seth mentioned, the style of eruptions at Mount Hood is really different than the style of eruptions at Mount St. Helens. Mount St. Helens is just kind of a jack of all trades. It's done tons of different things. It's lava flows. It's had big pyroclastic eruptions. It's had now 4 different huge debris avalanches. It's had 2 different lateral blasts. It does a lot of different things and has a wide variety of compositions that come out. Now Hood does the same thing kind of again and again and again and again and again. And so the nature of our forecast, I think, would be different in that there is a much more dominant scenario of activity that includes lava dome formation and ash-producing eruption, but not of the scale of something like Mount St. Helens 1980.
That's probably good news for us in Oregon. All right. So the next question is back to Mount St. Helens. Why does Mount St. Helens erupt so differently? The lava flow in the past to explosive Plinian type eruptions.
Good question. Let's see. Either what, if you want to do this, or should I do it?
You've already started, Heather.
Okay, so
Doing great.
yeah, so many eruptions. Let's take a step back. Magma reservoirs are the places where magma sits in the shallow crust. There are zones where magma accumulates, and the shapes and sizes of these zones can be very different from volcano to volcano. But all of them ultimately are fed from something deeper, and they don't appear magically out of nowhere. And so we might call this recharge magma, some intrusion coming from greater depth that comes up to shallow levels, and then in some cases sits around, crystallizes, and the magma may change composition as that crystallization proceeds. Okay, so part of the question of why magmas in general erupt of different compositions has to do with this issue of what is the stuff that's erupting? Is it the new magma that's coming in that somehow finds a pathway directly up to the surface? Or is an intrusion or some perturbation to the system actually just kicking the magma reservoir into erupting its magma, its different composition magma? So certainly part of the story is has to do with the magma chamber, the state of what's sitting there. What depth is it sitting at? How big is that reservoir? And then what's the nature of the intrusion that's coming in? And so, over Mount St. Helens history, there's evidence of intrusions, some that have much less signs of interaction with anything in the shallow crust, and others that have more evidence for crystallization, both in the deep crust and also in the shallow crust. It's not an easy question to answer. I think, the nature of of Mount St. Helens as a whole that I showed in some of those cartoons is that it doesn't always erupt from one single place. It erupts from a variety of different vent locations. Even the cone itself, if you look at the cone, there are domes that you can see protruding out the sides of the volcano. That 1857 eruption with the floating island lava flow, you saw the vent there didn't come from the top of the volcano. And because of this interesting geometry of how things can all come up, you could imagine that's also true at a bit greater depth. So some of it just has to do with the path, and some of it also has to do with what is the stuff that's coming up from depth to begin with. And it looks like at Mount St. Helens, that's just much more complicated. Whereas at Mount Hood, it seems to do the same thing, same path, more or less repeatedly. You guys can add things though if you want to there.
Sounds good to me, Heather.
Sorry, I was muted. Thanks. Let's see. So the next question is also about Mount St. Helens. They're both kind of the same question. So how many megaton equivalent was the lateral blast assumed to be? And the related question, kind of the same question, is does anyone know the amount of energy that was released during the eruption?
Ooh. What?
It's funny, Seth might know the answer to this, but I think he's answering the question on the other chat he's doing right now.
Yeah.
I have heard, so I don't have the number, but what I had heard stated was that the explosion on May 18th, 1980 released more energy than all of the munitions that were dropped in World War II, including the 2 atomic bombs. So that's not a megaton answer, but it might give you an idea of the scale of the explosion that occurred in 1980.
Yeah, that's probably an easier way of comprehending it than megaton numbers.
It was huge. It was huge.
Let's see. Another question. Let's see. If Mount St. Helens had erupted on the southward face of the mountain, what would have happened to Vancouver and Portland? How far would the blast zone have reached?
Well, of course, we can't know exactly how far the blast zone would have reached because part of the extent of the blast is the energy that was released by uncapping of the volcano, but part is just the geometry of what that slide scarp looks like. So how the vent intersects where there's now a hole. And so, you know, I guess one way to answer that question is to say, well, would it have looked just like it did to the south as it did to the north? Certainly, yeah, the geometry is a bit different on the south side than it is on the north. What the flanks of the volcano look like, that's a tough question to answer because because we don't know exactly how it would have slid, the landslide would have slid away. Maybe another way I can answer the question is by saying the previous blast in the history about 1,000 years ago, that lateral blast, that was directed to the northeast, and it was a much more narrow distribution. So the May 18th, 1980 blast reached 180 degrees of spread from the summit area. The lateral blast from 1,000 years ago was a much more narrow range of spread of directions from the volcano, and that's true from several other historic blasts, including one at Soufriere Hills and in Montserrat, and also another one at Merapi volcano in Indonesia. The spread was not quite as broad.
Was that other past, that lateral blast about 1,000 years ago, was that also triggered by an earthquake?
Gosh, triggered by an earthquake. 1,000 years ago, there isn't good record of that sequence, but that's a good question. It's not associated with as large of a big debris avalanche like this one was. So it could have been triggered by collapse of something else, a dome at the surface or something like that. But if an earthquake was involved, I don't know.
Sounds good. Let's see. So for the next question is about Vancouver. So for the question is, makes me think that the ground under our feet here in Vancouver isn't as solid as we would like to think. Does this add to earthquake danger close to Columbia River?
I mean, good question for Seth, but I think he's...
I just saw that Seth was on another call.
He's ducking the question. So the hazard for earthquakes anywhere in the Pacific Northwest is pretty high for these large Cascadia subduction zone events, which would happen just off the shore. Now, the farther away from the coastline you get, the less the shaking will be, but still in the Vancouver-Portland metro area, the shaking will be pretty intense. We sit on gravel deposits in Portland, Vancouver area that were deposited by giant floods that occurred during the last ice age, floods that roared out of the Columbia River Gorge and dropped the gravels that they were carrying through the gorge when they sort of spread out, when the water spread out when they hit the gorge mouth. And so that may result in a little bit more shaking because the deposits are not quite as consolidated. Solid rock tends to shake a little less in terms of the intensity of the shaking due to earthquakes. But whether or not it would make that much of a difference if there's a magnitude 9 just offshore, I think is maybe a bit debatable. That's going to, whenever that does happen, hopefully hundreds of years from now, that will be a pretty significant event, regardless of the kind of material that we're sitting on.
Let's see for the next question. Can you talk about why Mount St. Helens is not in geographic alignment with the rest of the Cascade volcanoes?
This is a good question for Seth.
Not it.
Oh my gosh.
I can come back to this question.
I think it's better if you do. There are some recent studies that actually speak to this question, and they're big studies and interesting, but I think Seth is probably the better person to speak to that.
Okay, I'll come back to the question. Let's see. So I think I saw it. we talked a little bit already about, you already talked a little bit about Mount Hood and Mount St. Helens. Oh, I just lost the question.
Ooh, I see Seth. He's back.
Okay, just in time. We have a question that's been directed to you, and that question is, can you talk about why Mount St. Helens is not in geographic alignment with the rest of the Cascade volcanoes?
You gotta unmute yourself.
There you go. Yep. Yeah, that's a really good question, and it's one that a lot of people gravitate towards, right? When you look at a map of the Cascades and you see St. Helens just kind of sticking out there, and it's an oddball location. It's in Cascade in volcanic arcs, you can get situations where you get volcanoes popping up behind the arc relative to the subducting the oceanic trench where the oceanic plates are subducting. That's providing the fuel for magmatic eruptions. But to have something that is closer to the trench is really weird. There's not many places in the Earth where that happens. And there's been a number of studies that have put ideas out there. They all have to do with the structure of the Earth that magma is moving through as it gets to the surface. And one of the ideas that's come out of a recent set of experiments that were collectively referred to as IMUSH, which stands for Imaging Magma Under St. Helens with a little case I, because we were cute. There is some idea that there's a large rock body, very, really large, like tens of kilometers on a side, called a batholith, which is basically a solidified magma chamber that was active millions and millions of years ago and has since solidified. And that's acting as basically a barrier for magma that's coming up, and it hits that and goes sideways, which is like a sill. And we know from the geologic record that there's sills everywhere, so that's not an unreasonable thing to think about. But basically, this is diverting it sideways and getting to and it goes sideways until it can get to a place where it can rise upwards again. And one of the things we also know about St. Helens is that it is located on top of something called the St. Helens seismic zone. It's this band of seismicity that goes relatively north-south through the volcano. There's no fault at the surface that anybody's been able to map that corresponds to those earthquakes, but they sure look like they're occurring along a fault. And one of the ideas that's been out there since the 1980s is that St. Helens is on top of a fault zone that is serving to focus magma coming upwards from underneath. And so those are some of the ideas, but really still there's not like the definitive answer. And to get the definitive answer is going to take, of course, a lot more work and study.
Let's see. Next question is, can you talk about the differences in equipment now? What can you measure now that you couldn't when Mount St. Helens erupted in 1980?
Whew. The question, it's what can't you measure now differently than it's actually the amazing thing about, from my perspective as a seismologist, one of the amazing things about that eruption is that from the seismic perspective, the monitoring there produced data that is still usable today using the same kinds of modern techniques. So that back then was the only form of real-time continuous monitoring that was available technologically. Everything else had to be done by people. And marching forward 40 years on the seismic side of things, the technology that's available is a lot better, that we're able to record on scale for a lot wider ranges. The instruments we're using are smaller, they're less power hungry, they're smarter. And so that means that it's easier for us to do the work out there. We can do more instruments, but that's just on the seismic side of things. And Mike, maybe you want to talk about the deformation and how radically things have changed since then.
Well, it really is gotten so much better. It doesn't so much involve people anymore out there making measurements. Back in 1980, there were these laser measurements that were taken to specific points on the volcano. you had to move the laser around and shoot various targets. It was very time intensive, and it had a fair amount of error. And there was a lot of uncertainty too, because you didn't know whether maybe you were moving towards the mountain or the mountain was moving towards you. You just knew the distance between the two areas was changing. Now we have the GPS system, which of course you may use in your cars or your phones or whatnot to see where you're going or guide you to a place. Well, we can use that to get millimeter level deformation anywhere there's a GPS sensor that is stuck into the ground. And we have something like 20 of these all around Mount St. Helens right now. So we can really image how the ground is moving at any given time. It's a continuous measurement. So if there were a bulge that we're forming today, rather than just having that one laser measurement on it that Dave Johnston was doing on May 17th in the morning of May 18th, we would have a whole network of like a web of sensors on the mountain that were reporting data back constantly. We would be able to see changes in real time all over the mountain. So our view has just gotten much, much better. And that's not even mentioning the satellite view, which of course adds a completely new dimension to everything.
Yeah, and if we could also mention the gas monitoring there, which in 1980 you saw some images of people making measurements with a spectrometer trying to measure rates of sulfur dioxide gas release. Now, not only do we have instruments that can do that on a continuous basis, but can also measure other gas species and the concentrations relative to each other. And so we're not just getting isolated snapshots, we're also getting continuous data and of many more species than just the sulfur dioxide that we were looking at in these tiny windows of time back then.
Let's see. Next question is, are we able to predict better the direction of the ash?
Ooh, that's a great question. Yeah, I think there have been huge advances. I don't think there have been huge advances on our modeling of ash dispersal. And so one of the models is a model by our USGS scientist who incorporates wind field data, so predictions of wind. And so we can make short-term forecasts of eruptions by inputting our ideas of scenarios of different explosive eruptions, the size of that eruption, and then use these weather forecast wind predictions combined with our scenarios to look at where the ash might be dispersed. That's a really great question because in the 1980 to 1986 sequence, different of these explosive eruptions went in different directions. There were some eruptions, very few of the eruptions that spread ash to the north, others that put ash on Portland, and then the very large eruption and the more majority of eruptions move ash towards the east. And so, yeah, wind direction is really important, and the modeling of ash dispersal has gotten really advanced in terms of its progress since those early days.
Cool, great. For the next question, is it safe to camp in the crater and I assume of Mount St. Helens?
Access is restricted to the crater of Mount St. Helens. You can't go into the crater without a special permit. Yeah, so it's a national monument, which is great. That designation offers a lot of opportunities for preservation of the landscape. It also restricts use in several areas of that landscape. And one of the restrictions is the crater area. That's a different answer than, is it safe to be there? There's no sign of anything happening in the crater volcanically right now, but there is, as I mentioned before, an advancing glacier that is now approaching the lip of the crater. And so even for those of us who go in to do research in the crater, there's a decreasing amount of landscape that is below the crater glacier front available for doing anything. And it's a thick glacier that has a lot of ice and rubble falling off. It's a very rocky glacier. There's a lot of material falling off the front of that. Gosh, there's a lot of ways we could go with this question.
Yeah. I think we can leave it at you're not really allowed to camp there.
You're not allowed to camp there. No.
There's really good reasons for why.
Yes. Let's see, from Simone, age 10, what is the biggest Mount St. Helens eruption so far?
Yeah, that's an eruption that people call the YN eruption. It's about 3,400 years ago. And it was many times the size of Mount St. Helens, May 18th, 1980 vertical eruption. Now, when I say it's many times the size, I'm really referring to that buoyant vertical portion of the column. I'm not talking about the debris avalanche or the lateral blast because that's a separate issue. Yeah, that's the biggest one.
All right, great. From Hudson, age 10, from Camas, Washington, what does dewatering mean?
Ooh, dewatering. When I talked about where the water came from for the lahars, dewatering means, imagine you have groundwater, water in the pore space, the empty space in any rocks beneath our feet, in any sediment. So dewatering means that the water moves through the permeable pathways in those rocks that form all of the hummocks in the debris avalanche deposit. The water moves through those pathways, dewatering the block. So expelling or losing its water by water migrating out of those pore pathways.
Great. Let's see, there's a Yellowstone question. So there's actually two Yellowstone questions. One is, what is the likelihood of an eruption for Yellowstone, and will we survive a Yellowstone eruption?
Want to take this, Heather? So these are questions I get an awful lot. I'm happy to answer them. So the likelihood of a Yellowstone eruption is incredibly small. The last time Yellowstone erupted, last time magma reached the surface of Yellowstone was 70,000 years ago. And that was a lava flow. And this is something, one of these great misconceptions about Yellowstone. Most people, because they see the doom and gloom documentaries, think that it only ever explodes. And in fact, Yellowstone, it's far more common to have lava flows than it is to have explosive eruptions. The last explosion was 631,000 years ago. But to put this in perspective, 70,000 years ago, Heather, can you tell us what Mount St. Helens looked like 70,000 years ago?
No.
No.
It basically wasn't there, right? I mean,
yeah.
So
yeah.
In the time since Yellowstone last had a magmatic eruption, Mount St. Helens became a volcano and erupted hugely many times. So Yellowstone doesn't erupt often, and when it does, it's usually a lava flow, which doesn't have a huge impact. Now, if it were to have a big explosion, and there's no sign of anything like that coming, in fact, the magma chamber beneath Yellowstone is mostly solid. We know this from looking at how seismic waves pass through the subsurface. But if there were to be a large explosion, yes, humanity would survive. And I say this with absolute certainty because this has happened before twice. We've already run this experiment. There was a large eruption in Indonesia 74,000 years ago, and there was a large eruption 26,500 years ago from New Zealand. Both of those were larger than the most recent big Yellowstone explosion. Humans were on the planet. And there's even recent evidence, there was some evidence from a while back that maybe there was a bottleneck in human evolution, that humans might have come close to going to extinct during one of those eruptions, but that's actually been mostly rebutted now. And it looks like humanity wasn't that impacted. Now, I'm not saying it would be pleasant. It would be incredibly unpleasant. We would have a lot of problems, but it would not be an extinction event as is often stated in poorly done documentaries.
They all say that, though, in the documentaries.
Well, they have to, right? I mean, they want you to watch, and you're not going to watch and say, yeah, you'll survive.
Yes.
People want to use the word super volcano.
They do.
Are you trying to push my buttons, Heather?
You just use the word super a lot. You're super.
Thanks. I dislike the term super volcano. I have a lot of reasons for it, but I think it's really kind of a trite term that doesn't actually reflect what the volcano does. If you want to use the term super eruption, okay, but I think there are really, just as one of my colleagues has said, there are volcanoes that have super eruptions, but there are no such things as super volcanoes. Sorry.
I like that.
Yeah. There's more questions, but we're out of time. But I will end with one last question because we definitely need to ask this one. This is from Selma, who is age 8. Is there such a thing as lava suits and lava boots?
Suits and lava boots.
Gosh, I love this question. Lava suits. There are reflective suits that people have used to sample lava. They're not suits you would want to wear to be indestructible to lava. Lava boots.
There are boots that people wear when they're sampling lava. They don't last very long.
They melt.
They melt or they get worn and torn and they go through pairs pretty quickly.
I would love to see a drawing of a lava suit and boot.
We were often asked, I was based in the Hawaiian Volcano Observatory for 10 years, and we were often asked, where's the silver suit? Where's the silver suit that you wear when you go out and sample lava? And we had one, but we used it more as a prop, because when you go out and sample lava, you don't actually need the silver suit in most conditions. There were a few places where it helped, where there was just so much lava that it helped. But for most of the times we went out to sample lava, we just wore gloves, and you want to wear natural fibers. In fact, sometimes we wore material that was sort of like what race car drivers wear, because if you wear polyester or synthetic fibers and those start getting warm, they can melt, and that's not something you want. So we always wore natural fibers and leather boots, and that was enough for lava sampling. But we did have a silver suit, just in case.
It's good to have that extra bling when you're out sampling, so.
Anytime, really.
It was a good Halloween costume.
Let's see, so we'll send the questions that we didn't get to, so we'll send them to y'all. And then if you have a chance to answer them, we'll post them somewhere on OMSI's, somewhere on OMSI's, one of their sites. I do want to ask if there's any last thoughts or questions or anything you want to tell us about that's going on, that's coming up as events at USGS and Cascade Volcano Observatory. Any last thoughts or anything you want to mention?
I'll mention that we would have had an open house this year. It got postponed, but that is a great way to come learn more about what's happening at the Cascades Volcano Observatory. It's postponed, but when it does happen, there are interactive exhibits, there are presentations. It's a day-long opportunity to engage with scientists at the Volcano Observatory and learn more.
And it's postponed to May of 2021. So fingers crossed that will happen.
Great. And so people, should they just check the CVO website then to figure out when that's going to be? Okay.
Yes, and the USGS Volcanoes Facebook and Twitter feeds, which will have things like that, as well as continuing the story of what was happening this time back in 1980.
Great. Awesome. Very cool. Let's see. So I did see a comment. So we'll post the answers to any of the other questions in the video comment section, and the video for this will be posted on OMSI's Facebook. So I do want to thank all of you so much for joining us, and I do want to give a big thanks to Dr. Wright, Moran, and Poland. You guys were fabulous. Thank you so much. This is such an excellent talk. And I'll just wrap up with a couple more things. But thank you guys so much. For the rest of the viewers, just to let y'all know, we are going to be posting this video, as I mentioned. It will be on OMSI's Facebook page and our YouTube channel. And if you're interested in finding out more about future Science Pub Talks, you can follow us on Facebook, Instagram, and Twitter. If you are interested in donating, you can make donations using the Facebook donate button, or visit us at omsi.edu/donate. Next week, we've got a really great lecture lined up. On Tuesday, May 26th, you can join us to learn more about the exciting world of stop motion animation with our local award-winning movie studio, Leica. So that should be really fun. And then on Thursday, May 28th, we'll learn about American elections, what special challenges the pandemic presents, and ways that data science can help verify election results. I also want to give a big thanks to our partner, Stellastream, for hosting this the video live video streaming. We wouldn't be able to do it without you. So thank you so much for making tonight's event possible. And if you're interested in more information, you can always go to OMSI's website at omsi.edu/sciencepub. So thank you everyone for joining us tonight. Have a great night and the rest of your week, and everyone stay safe. Take care. Bye.